Then let me introduce the next speaker. He's Gereon from Certora, a researcher there, and he will give us a talk about formal verification in the context of finite fields. So, does it work? Yeah. Okay.
So, I have to say two things beforehand. I love the scheduling, because I'm the formal verification guy that will now tell you that fuzzing is totally inappropriate. No, just kidding. Yeah, I'm from the formal verification side, and you will now hear a two-part talk, because I was kind of asked for like two topics, and there was a bit of back and forth, and I ended up presenting both. So, but I hope you'll enjoy both. So I'm Gereon. I used to work for Stanford, and the work there is the first part. And now I work at Certora, where we build a formal verification prover for EVM. And this will be the second part, where I quickly show you what we do there and how you can use it. So, and this will be our agenda. I quickly say something about formal verification, and then we go into finite fields, what you can use it for, and what we did to allow you argue about finite fields. And then I'll show you quickly the architecture of our prover and how you write specifications. Pretty much like how you write fuzz tests, as you will see. So formal verification, I guess I can pretty much skip the slide for now, because it's pretty much what you have seen before with this nice pyramid. So I did frame it in the case of why do you trust your code, and it's pretty much the same bullet points you already saw. And if you do all that, that's great, but of course, if you come for more theoretical side, or you have very high standards for your code, let's see what the problem is here. White box testing might not be enough, because you still have problems that you can miss certain cases for a variety of reasons, be it because they're just very rare, but well, a good attacker might still find them. Maybe you run into some of these cases where you actually suffer from a not that exact interpretation of the Solidity code, whatever, but maybe you want a formal proof that what you're doing is correct. So what formal verification does basically is you have your system in what way you want. So for example, let's say you have Solidity code and you have a specification. And the specification is some way to say what you expect your system to do, what kind of invariance it should have, stuff like that. And then you do some magic, and either you get a proof of correctness, and this should be like a mathematical proof that whatever your system is satisfies the specification and does not go outside of the specification, or you get a violation, which then would be a bug that you should fix. And formal verification is the magic in between. Well, and of course, it's not magic. There's a lot of work there. So what we do is we select a logical framework that is suitable to describe both your system and the specification. And then we encode within this logical framework the system and the specification to some kind of formula. And depending on what system you have, what specification, there are different flavors for what this logic can be. And then you solve that logical statement, or usually, like the formally correct term, we decide that statement and interpret the results. And what happens in there is a lot of math, a lot of work, sweat and tears. It can be really frustrating. It's sometimes slow to do in practice, but if you want to have a really proper proof here, like you want to have a proper statement that tells you there is no bug with respect to your specification, this is the way to go. So that's the problem with fuzzing. It can never tell you there is no bug. So, and yeah, it's sometimes slow, sometimes it doesn't really work for a variety of reasons, but if it works, it's really great. So, and with that, I go to the first part, which is Satisfiability Modulo Fields. And if you don't understand any of these words, well, not that bad. Think zero knowledge proofs. We have got a lot about them. Think ZK snarks, and we want to argue about ZK snarks. And for example, if you have a framework to build these tools, for example, Socrates, then we want to one application is to show that the intermediate steps that Socrates does to minimize the circuit, for example, are actually sound, and there are no bugs there. And actually, this has been used to find bugs in these compilers. The underlying paper is exactly called Satisfiability Modulo Fields. Great credits to Alex Ostermeer, who did the main work here, and I consulted on this and did a bit of the research work, but the main work is really from Alex. So, this is a slide where I explain what ZK snarks is. My expectation is that at least 2/3 of the people in the room know better what this is than I do. So it's a zero knowledge, succinct, non-interactive argument of knowledge. So it's a zero knowledge proof. It's very short, which is great. It's non-interactive, so you can just post this on the blockchain and you don't have this usual protocol going on. There are a couple of applications, like you want to have some transaction information private, just for the sake of privacy. It can also be used to mitigate MEV attacks because certain stuff is private that cannot be exploited. You can verify off-chain operations. Yeah. The experts on these applications are over there and not here, really. But the important part is, in the end, the technology of ZK snarks in the end are relatively simple circuits over finite field elements. And circuits with that, these are usually equations of polynomials where variables are from a finite field. And I'll explain to you in a minute what finite fields means exactly, because this is like the critical point. And what we can do then is we solve these circuits for a specific definition of solving. Usually it means we show equivalence of two circuits. And if we find a violation, that means they were in fact not equivalent, and this indicates a compiler bug. So, what is a finite field? So a field is a set of numbers, usually, where you have addition, multiplication, and inverses for both of them. And you probably know complex numbers, real numbers, rational numbers, whole numbers, I don't know. But maybe you have also seen stuff like these Z7 or Z modulo 7 or Z modulo 7Z. There are various ways, which is just the numbers from 0 to 6, and then you have a wraparound, so a modulo. Or maybe you have even seen something like the rational numbers adjoined with the square root of 2. So that's a way to build a greater set of numbers that has all the rationals, but also square roots of 2, and you can work with them. Either way, all these are fields, and now, maybe not that surprising, finite fields are fields with finitely many elements. And if we look here, all of these are obviously not finite. There are infinitely many numbers in Z, in the rational numbers, in the real numbers, and so on.
Is it a mistake that these are not a field?
Yeah, you're totally right. Oh my god. Yeah, Z should be not here. Yeah. Z is not a field, of course. So, with finitely many elements, right? And now you could say, okay, there are very many different fields with different characteristics, not in the strictly algebraic sense necessarily. The interesting thing with finite fields is that there is a very strict categorization. So for every Q, where Q is a prime number to some exponent, there is a unique finite field up to isomorphism. But for all practical purposes, it's a unique thing. And that means it's really, if you say me if you tell me what Q, so how many elements you want, it's clear what field you're talking about. It's unique. And then there are basically two cases of fields. Either the k, like the exponent, is 1, then we're talking about prime fields, and then we really have the natural numbers modulo usually a big prime, and this is what you will see in many crypto systems. If you say k is greater than 1, then you have a field that comes out of a somewhat unintuitive construction. So if you study pure math in algebra, it's a supernatural thing that happens there. For everyone else, it's something super weird. So you have your prime field as a base field, and so you build a polynomial ring, and you get a irreducible polynomial of degree k, and you have the factor ring or quotient ring. So it doesn't matter. The important thing is it's not doing what you think it does. So if you think, okay, I take fq, and as q I take 2 to the power of 64, it's not your 64-bit integer. It's something completely different, and thus, for most cases, completely useless. Sorry to all the algebra people. So for the purpose of this talk, whenever I say finite field, I mean a finite prime field. And most of the time, because that's what most of the crypto applications are doing, we do fp with a big prime. So that's what you usually see. So how do we solve these circuits? So I come from a field that's called Satisfiability Modulo Theories. That's a specific solving approach. The main question we deal with is we have a formula. That's a first order formula. So that purely existential. That means you have Boolean combinations. So you have AND or negation, and then you have constraints from a certain theory, and our theory will be equalities over finite fields. And we ask the question, is there a solution, in the sense, is there a variable assignment such that the formula evaluates to true? And what we usually do is we get this formula, and then we have a subsolver that deals purely with the Boolean part, and we have one or more theory solvers that deal just with sets of these theory constraints. And then they interact, they talk to each other, so the subsolver works in the Boolean part, and it asks the theory solver, is that fine? And the theory solver will say, well, no, that's not fine, and they go around. And in the end, it tells you either, yes, there is such a solution, and by the way, here it is, use this assignment, or tells you, no, there's no solution. And depending on which solver you use and what the exact theory was, it can also tell you quite a bit about why there is no solution. So it can tell you some kind of proof in some level of detail. So, and that means if we wanna show that two of these circuits are equivalent, the only thing we need to do is implement a theory solver for equalities over polynomials over finite fields. Okay, let's do that. So this is exactly what we have here. We have a number of equalities where f1 to n are polynomials, and x are variables over finite fields. And well, I come somewhat from algebra. So when you come from computer algebra and you have some polynomials, you throw that at a Griffin basis. That's always what you do. It's the main workers of computer algebra. It's in theory, the complexity is pretty bad. So most people have a hard time even imagining what W exponential is. So if you think you know exponential growth, yeah, that's W exponential is way worse. But in practice, it's pretty efficient. And what it essentially does is it keeps the set of solutions the same, but gives you a simpler representation. So it kind of transforms the set of polynomials that are in there so that you have an easier time figuring out what's going on there. And the core question we usually ask, is there a 1 in there? So if 1 as a polynomial is in the Griffin basis, that means there is no common solution, because 1 equal to 0 is false, which means if the one polynomial shows up in the Griffin basis, we know there is no solution, and we have 1. So, and this is exactly if after the Gereon base we see we have this one polynomial, we have answered, and it usually means we have verified that our problem holds. That's great. But when one is not in the Gereon basis, we would like to say it's SAT, but unfortunately, Gereon bases are only complete in the sense that we want on complex numbers or technically algebraically closed fields. So then we mount a backtracking search. And essentially, if you are pessimistic, we do a brute force search over the whole assignment. And that's kind of, well, we haven't won anything. But by virtue of the structure that the Gereon basis gives us, so you kind of get a triangle under the proper ordering, variable ordering, you get kind of a triangular structure, and the backtracking search can exploit that very efficiently. So it's still, in worst case, it's horrible, no doubt about that, but it's surprisingly efficient in practice. And so we implemented that in CBC5, which is the SMT solver from Stanford and one of the two leading SMT solvers. The other one would be Z3, I would argue. We took two specific conditions, soundness and correctness, from three compilers, from Socrates, Zoc, Circ, and Circ, which Circ is a framework from that was developed at Stanford as well. And we implemented this approach in CBC5 to check these conditions, and we compared it against other encodings, because of course you could argue, yeah, well, why should you use this approach? The other approaches would be to encode it as regular integers, and then after each operation do modulo p. You could also encode it as bit vectors, so if you know about how encoding in SMT solvers work, it might be a good idea. So Z3 is kind of the best solver you can use for NIA right now, at least for these types of questions. Bitwuser would be the leading bit vector solver. And we also skipped the whole SMT part and just directly threw it as a computer algebra solution there. So, but then you have to encode the Boolean structure into computer algebra as well. And the results are pretty nice. So you see, these are the other three encodings. So we had like 800 something benchmarks. And you see here, how many benchmarks could we solve within some amount of seconds. And so the further to the bottom right you get, kind of where the curve is, the better it is. And the other three encodings are somewhere over here, and we do way better. So that's pretty nice. So if you have such problems, have an application for that, if you want to argue about finite field equations, yeah, please check out CBC5. It's great. Alex has done some great work there. Okay. So with that, I go to the other topic, the Certora Prover, and this is now essentially the equivalent of what Joseph just told you, a tool for fuzzing. I will now show you a tool for formal verification. And this is the picture from before. The bird's eye view, we have here our Solidity code, we have our own spec language. Then our prover takes these two, and you get either a proof that the behavior meets the specs. Truth be told, the proof is kind of implicit by virtue of our prover telling you everything is okay. We don't actually generate a proof certificate you could feed to Isabel or Coq or whatever. Or we give you a behavior which violates the spec, and I will show you in a minute how that looks like in practice. So what do we do internally? And that also was the motivation for my question beforehand. If you mount the effort to do proper formal verification, you actually want to verify the real thing that runs on the blockchain. And thus we start with Solidity, but then we run the standard Solci compiler. So we run the standard compiler toolchain with your compilation arguments. We get the EVM bytecode, and actually we can also take the EVM bytecode right from the blockchain and run on that one. But then, well, we can't show you the Solidity code that led to the bytecode. So the backtrace in the end of the counter example will be kind of useless. So usually people use it from the Solidity code. And then we have a decompiler. By the way, this also means that we occasionally find bugs in the Solidity compiler. So that's a nice side benefit. We also have support for EVM bytecode, for other EVM languages. So if you want to have another way to get your EVM bytecode, that's fine. You can, for example, use Viper. We are also working on other bytecode. So, for example, we're working on Solana support and WASM support, but that's really experimental proof of concept phase right now. So, after that is done, after we went through the decompiler, we, as every such tool, have our own intermediate representation that we call TUC, which is 3 address code, very imaginative. And it's kind of a assembly style language that fits our needs. And then it's so that it's a bit easier for us to analyze a lot of stuff. So we then go into an analysis phase to recover memory layout, memory segmentation, pointer relations, for example, to figure out which functions are called. We have support for hooks and summaries, so that you can get a hook would be like you get a some of your code is called whenever some memory changes. So whenever someone writes or reads from a Solidity variable, then some of your code is executed, so you can do some stuff. Summaries would be to abstract away functions that are very hard to analyze, so you can give like a formal description what the formula does. Typically, people will write square root functions in Solidity that may be very efficient, but are a pain to analyze. And so you can then go there and add a summary that tells the solver, yeah, it actually computes the square root function, and then you can use that for the full proof, and then you can separately prove that the function actually computes the square root, and that's a big help. Yeah, and then you do this typical static analysis stuff. You do pruning, you do inlining, you do all the stuff. And then we merge the program, the contract code, with the spec. So all this gets folded into one program, and essentially this will add assertions to the contract code in a specific way based on what your specification was. Then we do another round of static inlining. And then we start with a traditional formal verification thing. So we encode this program into a verification condition, which is essentially a logical formula. There are some intermediate steps there, but whatever. And this logical formula we then take to a SMT solver. The SMT solver will tell us either, yeah, that's good, or I have a counterexample. And if there's a counterexample, then there is a whole machinery to actually turn just the assignment to variables from the SMT formula into a backtrace you might expect from a debugger-like interface for your Solidity code. Okay, so, and now I'll show you quickly how these specs look like, and I hope to convince you that writing specs is not really, I mean, it is the crux of formal verification. So even if the formal verification tool is perfect, if your spec is wrong, the whole exercise is pointless, but it's still somewhat nice to use. So let's start a very simple example. We have a small bank, so the simplest Solidity bank you can imagine. You have some funds, you can get the funds, you can deposit, and it's a small bank because we say, well, here we can only deposit so much that the total funds are not above, I think it was 2 to the 64, but it doesn't matter. So it's some threshold. And then you can transfer and withdraw and whatever. So, and now you want to show some invariance. So maybe you want to know, does it actually work? Like, does the deposit work? Does actually depositing increase the funds? Can there be some overflow, maybe? So can I somehow break this very basic thing? and then you write a spec, and that's all it takes. So you have what we call a rule, and I usually think of it as a unit test case. So think about it as a unit test where you get the funds beforehand, and let's just say I, as a sender of the message, want to check my own account. So I get my funds, then I deposit some amount, I get my funds again, and I expect that after the deposit, my funds are the funds before the deposit plus the amount. So what's different from a regular test case? Neither the amount nor the execution environment, which is essentially the state of the blockchain at that point, is fixed. And where the fuzzer will now go around and try a lot of values for amount, we will mount a proof that it holds for all values of amount and all values of the environment. And that's basically what's happening. And in this case, as I'm a developer, I will usually run it on the command line, and you will get a nice-ish command line output that tells me, yeah, the rule is not violated. Great. And then you can either go around and check whether the rule is really right if you expect a violation, or you're happy. Okay, can others withdraw from a bank? Well, I've written the code, you should trust me. But you can also see, okay, there's withdraw from. But maybe the code has a lot of functions you don't really know. So you write, there's a nice feature. You can have a variable of type method. And what we will do is we will instantiate it for every function that is in scope. So that exists in the contract or any of the contracts that is currently in scope. So what we do is we say, okay, there is some other address that is not myself because we wanted to check whether I can withdraw from someone else. We get the funds beforehand, and then we do any function call. Call data args is anything now. The function, the method is anything. So we call any function with any argument that is there. Then we get the funds again, and we check whether we could decrease the funds of this other address. And what we'll see now is we will have results for this rule name, and it actually split out into a bunch of sub-rules. Most of them worked, but there is this withdraw from method, which does exactly what the name suggests. I can withdraw from other accounts. And it will tell me, yeah, this is violated. And now, of course, the obvious question is, how was it violated? In this case, it's probably easy enough. You look at the function, it's a one-line implementation, and it's stupid. But in general, now you will see, you will usually, as a regular user, will get a web report. This is essentially just the table that is also in the command line. But you will also get a call trace, and so you can see, okay, what exactly is executed. So the details are not really important, but you start with the global state, and then you have the rule code. So that's a require. You get the funds, then you call the function, and then it tells you, okay, for this violation, what function did I call? Oh, I called withdraw from with this variable argument, with this argument, with these values for these arguments, and it tells you exactly, okay, which branch conditions were executed, what internal function calls were executed. At several places you can then see, okay, what is the global state at this point in my call trace, and it should be a great help to actually figure out what was going on there. And as a last feature that is oftentimes very convenient, invariance. So for example, I claimed it's a small bank. So maybe we want to check that funds can never grow beyond this constant I've enforced there. And we can immediately see, okay, there's a require, so there is we make sure that we can never deposit that much. So we can never go beyond this limit by depositing, but okay, does it hold for the whole system? And so what we can do is we define an invariant, and invariants are automatically, so the way they work is, first we assume the invariant, then we call any function with any arguments, and then we check the invariant still holds. And this, as a common use case, and people get tired of writing this down all the time, we have a nice utility for that. We just say invariant to give it a name, and you just state the property. And the property is get funds for my account, but as the environment is instantiated with all values, it means all accounts are below that. And, well, I'm not a good Solidity programmer, so I, of course, didn't check the property in the transfer method. So what you'll see is, yeah, you can transfer and thereby break this property. And again, you get a nice call phrase. You see exactly what's going on. We assume the invariant in the pre-state, and then we call some function. We call transfer with a ridiculous amount, and then we assert the invariant in X breaks. So, and that's how it looks if it works. One last thing, a quick advertisement. We are currently doing like a formal verification competition where you are supposed to verify or break properties on Uniswap optimally using our prover. That would be great. There's a prize pool. If you're interested, go ahead, check it out. Otherwise, I'm happy to take questions.
Yeah.
Thank you very much.